Hello everyone, I am Vinay MS. Today I am going to give technical seminar on friction stir welding. These are the contents of friction stir welding: principle of operation, microstructural features, parameters, generation of heat, welding forces, applications, advantages and disadvantages. First we go to the principle of operation. In friction stir welding, a cylindrical shoulder tool with a profiled threaded nib is made to rotate. The tool is rotated at a constant speed and feed at a constant transverse rate into the joint line between the two pieces. The two pieces are clamped rigidly onto a backing bar in order to prevent the abutting joint faces from being forced away. The heat is generated between the wire resistance welding tool and the material. This heat, along with the heat generated by mechanical mixing and the adiabatic heat within the material, cause the material to soften without reaching the melting point. The leading phases of the pin forces the plasticized material to back off the pin while applying force to consolidate the weld metal. Next we go to the microstructure features. The solid state nature of process combined with its unusual tool and the asymmetric nature results in highly characteristic microstructure. The microstructure can be broken into the following zones: stir zone, flow arm zone, thermomechanically affected zone, and heat affected zone. First we go to the stir zone. Stir zone is a region of heavily deformed region that corresponds to the location of pin during welding. The grains within the stir zone are roughly accessed and often an order of magnitude smaller than the grains in the parental material. A unique feature of stir zone is common occurrence of several concentric rings which are uh, which are referred to as an onion ring structure. Next, flow arm zone. It is a region corresponds to upper surface of the weld that consists of material dragged by the shoulder from the retreating side of the weld around the rear of the tool and deposited to the advancing side. Next we go to the thermomechanically affected zone. Thermomechanically affected zone occurs on either side of the stir zone. In this region, the strain and the temperature are less and effect of welding on the microstructure is correspondingly smaller. Unlike the stir zone of the microstructure recognizably that of the parent material significantly deformed and rotated all through the thermomechanically affected zone. Technically refers to the entire deformed zone. Often it is used to describe any region not already covered by the terms stir zone and flow arm. Next we can go to the heat affected zone. In heat affected zone, this region subjected to the thermal cycle but not deformed during welding. The temperature are much lower than the thermomechanically affected zone, but still has significant effect if microstructure is thermally unstable. Next we go to the welding parameters: tool rotation and transfer speed. Increase in rotational speed and decrease in the transfer speed resultant in hotter weld to produce successful weld. If the material is too cold, then voids or flows may be present and tool may break. Next, coming to the tool design. The design of the tool is creative factor. Good tool can increase the good quality weld. Tool material must be strong, tough and hard wiring at welding temperature. It should have good oxidizing resistance and low low thermal conductivity to minimize heat loss and thermal damage. And these are the different types of tool design: straight cylindrical, threaded cylindrical, tapered cylindrical, square cylindrical, and triangle cylindrical. Next we go to tool tilt and plunge depth. Plunge depth, uh, plunge depth is defined as the depth of the lowest point of the shoulder below the surface of welded plate. Plunging the tool below the plate surface increases the pressure below the tool and produces enough forging of the material. Excessive plunge depth may result in flows in the weld. On the on the other hand, excessive plunge depth result in the rubbing of pin and packing plate surface. Next we go to the generation of heat in the welding. Heat generation during FSW arises due to the two main reasons: friction at the surface of tool and deformation of the material around the tool. Heat generation is often assumed to occur predominantly under the shoulder due to its large contact area, and equal forces are required to overcome the contact force between the tool and the workpiece. The contact condition under the shoulder can be described by sliding friction. Mathematically, approximation for the total heat generated by the tool shoulder is given by Q total is equal to 2 divided by 3 into pi P into mu omega into capital R cube minus small r cube. For sliding, for sticking, Q total is equal to 2 by 3 into pi tau omega into capital R cube minus small r cube, where omega is the angular velocity of the tool, capital R is the radius of the tool, and smaller is the pin. The major difficulty in applying these equations is determining suitable values for the friction coefficient or the interfacial shear stress. The conditions under the tool are both extreme and very difficult to measure. To date, these parameters have been used for fitting parameters, where the model works back from measured thermal data to obtain the responsible simulated thermal field. While this approach is useful for creating process models to predict, for example, residual stresses, it is less useful for providing insights into the process itself. Next, coming to the welding process. A downwards force is necessary to maintain the position of the tool at or below the weld surface. A transverse force acts parallel to the tool motion and is positive in a transverse direction. This force decreases as temperature around the tool is increased. The lateral force may act perpendicular to the tool transfer directions. Torque is required to rotate the tool, the amount which depends on downward force and the friction coefficient. Next, coming to the applications: shipbuilding and offshore, aerospace, automotive industries, and railway rolling stocks. Coming to the advantages and disadvantages of friction stir welding. Advantages are good machine properties, improved safety due to absence of toxic fumes, no filler or gas shield is required, easy automated and simple milling machine. It can be operated in all positions, horizontal and vertical, etc. Low environmental impact, good surface finish. It does not require further machining. And coming to the disadvantages: exit hole is left when tool is withdrawn. Large down force is required with heavy duty clamping to hold the material. Less flexible than manual and arc weld. Thank you.